So it said for each expression, write something that reveals what it represents. So in other words, you see this, think what? See this, think what?
The general formula.
Okay, but what when you see these symbols,
Oh, right, a list.
a list, right? So when you see that this is a list, it's a sequence, right? It's a sequence, it's a list. So let's write out the list. So how do we generate the list? Well, I will start at 1 for the first term of the list, and then if it's an infinite sequence, we'll just keep going on and on and on. So when I is 1, we get 1/3. When I is 2, what do we get?
A ninth.
Ninth. When I is 3, we get 1/27th. So we're getting powers of 3 in the denominator. So you see this, you think this immediately, right? Think, oh, that's a list. I can generate the list by letting I be 1, letting I be 2, letting I be 3, etc. And I get this list. What kind of sequence is this?
Geometric.
Good. So this is our geometric series. Or sequence. We just mentioned this at the end of class, just the form of it, and we're going to take a minute after this slide to delve a little bit deeper into geometric sequences. But we know that if it's a constant raised to the I, the index, that's a geometric. Okay, what list is this? Same thing, I equals 1, we get a number, we get 1. When I is 2, we get so 1/3 power is cube root, right? So we're going to get the cube root of 2, then we're going to get the cube root of 3, and the cube root of 4, etc. And keep going like that. Right? So these are lists that are generated by I taking on the counting numbers 1, 2, 3, 4, and then the formula tells us what the ith term in the list is. What kind of sequence is this?
P sequence.
We said so. This one we looked at a little more in depth last time. A P sequence. So what's our value of P here? P equals
Pi or 1/3.
1/3. Right? P is 1/3. It's the exponent in the denominator of the index, right? The exponent of the index in the denominator. So it's 1/3. And so we talked last time about will this converge or diverge, this sequence then? What was our rule for the P sequence?
Sorry, I converged to 0.
As long as P is greater than 0, as long as that exponent is positive, doesn't matter how small it is, as long as it's positive, the sequence converges to 0. Meaning, as long as that exponent's positive, your denominator is going to get infinitely large. Right? Even if it's a fraction like this, 1/3. So any positive exponent means that your denominator keeps getting larger and larger without bound. So your fractions will get smaller and smaller, and eventually so close to 0 that we can't tell the difference. Okay, questions on any of this slide? So we have not talked about convergence of a geometric sequence yet. Let's take a look at this one. This one going to converge or not?
Yes.
Just kind of from observation. Yeah, we got powers, powers of 3 in the denominator. We know those are going to get big. In fact, they're going to get big fast. So this one converges to 0. So let's try to come up with a general idea of for what. This is actually called R. We call this R. So this is R to the I. For what values of R, our base, will the geometric sequence converge? Let's take a look at that. Questions before we go on?
Yes, sorry. R is equal to 3 or R is equal to 1/3?
That was 1/3 in that case, because geometric sequence is this, R to the I. So it's on some number raised to the I power. So the question we're asking is for what values of R will R to the I get really small? Like infinitely, get closer and closer and closer to 0. Or get really big, or stay constant, or do something else. So let's just investigate some examples here. So what about 1 to the I? What sequence is that? 1 to the I. 1 to any power is?
Sequence.
1 to any power is 1, right? So that's just going to be the sequence of 1s. Does it converge? Is that a convergent? Does that sequence converge?
No.
No.
Does it hone in on a particular value? Does it get indistinguishably close to a value?
Yes.
Yes, 1, right? So that converges to 1. It's like, it is 1s, right? So it's unmistakably converges to 1. All right, what about this? 2 to the I. What does this look like? First term is 2, then
4.
4,
8.
8,
Yeah, it's just
16.
the exponents of 2.
Exponents of 2. Converge or diverge? Diverges, just gets big without bound, right? Let's just keep, you're always multiplying by 2. And so this is the idea of a geometric sequence, that to get the next term, what do you do? What do you always do to get the next term of a geometric sequence? I had 2, now it's 2 squared. I have 2 squared, now it's 2 cubed.
Multiplied by r.
Yeah, good. So you always have one more r that you're multiplying by. So to get to the next term, you multiply by r. In this case, r is 2. That's the idea of a geometric sequence. You keep multiplying by r to get the next one. So this one diverges because powers of 2 will get very big and never stop getting bigger. Okay, next one, 3/4. 3/4, then 3/4 squared, 9/16. 3/4 cubed, 27/64, etc. So what's happening, we're always multiplying by 3/4. So what's happening to this list of numbers? Increasing or decreasing?
Decreasing.
Always taking 3/4 of the previous value. So it's going to decrease. Converge or diverge?
Converge.
Converges to 0, right? This is going to converge to 0. If you're always taking 3/4 of the previous value, keep 3/4 times 3/4. Always taking 3/4, then that's going to get very small. And as small as you want it to get. Okay, what about -1/5? So -1/5, then +1/25, then -1/125, then +1/625, etc. Converge or diverge?
Converge to 0.
Definitely converge to 0, right? And again, our denominator is getting really, really massive and will never stop getting big, so these fractions will never stop getting closer to 0. The fact that it alternates doesn't really matter. It's just going to, if you imagine a graph, the numbers will get closer and they're going to hover on either side of the horizontal axis, but still honing in on 0, even as it does from kind of both sides, from the bottom and from the top. Okay, so we're seeing a pattern. What about this? Without writing out the terms, converge or diverge?
Diverge.
Diverge.
Yeah, so this is going to diverge badly, right? Because it's going to always be multiplying by -3. So it's going to be 3 times as big, but then it's going to be alternating negative, positive, negative, positive. So if you think of a graph of that one, it's going to be like this. So it's kind of diverging in both directions. Like it's getting super large positive every other term and then super large negative every other term. So this diverges badly. What about this? -1, 1, -1, 1, -1. Converge or diverge?
Diverge.
we said that if it doesn't converge, if a sequence does not hone in on a one particular value, then any other situation diverges. Here's one such situation. So sometimes students think, oh, that's converging to 0 because it's like the average. But no, that these terms of this sequence never get close to anything. They keep hopping back and forth between 1 and -1. So they never get indistinguishably close from one number. So here's an example of a sequence that can diverge without getting really big, right? So a lot of our examples of series that diverge, the numbers just get really big positive and without bound, or really big negative without bound. But here's an example of one that's not like that, but still diverges. It's kind of hopping around. Okay, so let's kind of put these examples together and come up with a scheme. So for what values of r, would these terms get very, very small, in fact, indistinguishably close to 0? What values of r?
I was going to say when their absolute value is less than 1.
Okay, so that would mean r is less than 1, for instance, this example here. But we also saw negatives that are, in magnitude less than -1 also work. So what about this? What about when r equals, so if where r is between -1 and 1, then converges to what value?
0.
But there's one kind of standalone case. We also saw it converges.
R equals 1.
Yeah, this first one, when r equals 1, that's the only it's kind of a trivial case because you get a list of all ones that converges to 1. So the interesting case here is this one. If r is between -1 and 1, we keep taking like a percent or a fraction of what you had before. So if you do that, infinitely, it's just gonna hone in on 0. And if r is greater than 1 and less than -1, you're just gonna fly off to big numbers, right? Because you keep multiplying by 2 or 3 or something bigger than 1.
Professor, can we ask a question?
Of course.
So just to clarify, for -1 to the power of I, we're also going to say that diverges as well?
Anything that doesn't hone in on one particular value, that's what converges means. If it hones in on one particular value, gets indistinguishably close to one value, that converges. Anything else diverges.
Thank you.
Yeah. All right, so we say that the sequence converges to 0 as I gets big if r is between -1 and 1. And that's our focus case. That's our interesting case. We also have this case, which is kind of trivial, right? So if r equals 1, we just get the list of all ones, and that converges to 1. Okay, so p sequences converge to 0 when p is greater than 0. Geometric sequences converge when r to 0 when r is between -1 and 1. So these are just facts that you have to file away. You have to be able to recognize those sequences and then know those facts that we've kind of deduced here. Questions on geometric sequences? And again, the idea of a geometric sequence is to get the next value in the list, you're always multiplying by r, right? So it's always one more r multiplied to get the next value, next term in the list. Okay, so let's talk about another technique for analyzing sequences, and that is L'Hopital's. It's called L'Hopital's rule. And so L'Hopital's rule is normally used for continuous functions, but it works perfectly good for sequences too, because it's just with a sequence you're just looking at discrete values. Whereas a function, you're looking at continuous values, but it's the same effect in the end. So as x gets very large, a function that's a ratio of two functions. Now, this isn't necessarily a rational function. It's going to be a function of a quotient of any two functions. If that quotient has one of these two forms, infinity over infinity or 0 over 0, then these are called indeterminate forms. Because there are situations where these can be infinity, where these could be 0, where these could be some constant value. So there really anything's possible when you have one of these indeterminate forms of infinity over infinity or 0 over 0. It depends on the situation. So to help you solve that, L'Hopital's rule says that the limiting value of the ratio of the derivatives will be the same as the limiting value of our original ratio. So what we can do is we can take the derivative of the numerator and the denominator and set up a new ratio and analyze that. And whatever that does will be the same as what our original function does. Okay? This is not the quotient rule, right? The quotient rule is more complicated than that. L'Hopital's rule lets you just take the derivative of the top minus and the derivative of the bottom, set up a new problem, and the resulting limit of that will be the same as the limit of the one we started with. So for example, 3i plus 1 over e to the 1/2 I. Okay, so it's not a p-sequence, it's not a geometric sequence, it's not a plain rational function. So, but we see that as I goes to infinity, what would the top do?
Go to infinity.
Yeah. And what would the bottom do?
Also go to infinity.
Yeah, so we have this indeterminate form that your numerator is going to get really big and your denominator is going to get really big. So by L'Hopital's rule, we can look at the derivative of the numerator divided by the derivative of the denominator. What's the derivative of the numerator?
3.
3. Derivative of the denominator is?
1/2 e 1/2 I.
Right, chain rule. 1/2 e to the 1/2 I. And so, what about this? As I goes to infinity, this thing does what?
Converges to 0.
0, right? This is an exponential function. As I gets big, this is going to get super big. Definitely goes to 0. Therefore, since the ratio of the derivatives goes to 0, this will also go to 0. That's what L'Hopital's rule says. So this sequence converges to 0. Okay, questions on L'Hopital's rule. So if you analyze, you have a ratio of two functions and you analyze, you take a look at what's happening in the numerator and the denominator and you get infinity over infinity or 0 over 0, you can apply taking the derivative of the top and the bottom and working on that problem. Sometimes when you do you do those derivatives, you'll get infinity over infinity or 0 over 0 again. And then you can do it again. You can do second derivatives until you no longer get one of the indeterminate forms, and then whatever you do get will be the same limit as the original problem. Okay, questions on that?
Sorry, can you use this on natural log functions, or would that be a different rule?
As long as the ratio as your index gets big, as long as the ratio is infinity over infinity or 0 over 0, you can use it.
Okay, thank you.
Yep.
Does negative infinity work too?
Yeah, so yeah, these are, yes, exactly. So then a negative on one or both of these, that wouldn't matter. Okay. So let's look at, let's talk about analyzing sequences for convergence and divergence. That's what we're doing here. And so we're starting to build like some tools here. And the idea is that you come to a sequence and you have to figure out which tool to use. Okay? And so here's kind of a little bullet point list for you. So first of all, look for your geometric and p-sequences. So you're on the lookout for those. And we know when the geometric sequence converges, when r is between -1 and 1, converges to 0. And p-sequences converge when p is greater than 0. So we'd be on the lookout for those. All right? Next is use the function limit techniques. Okay, so properties of rational functions. So we saw one example of this last time. So a rational function is like, so we had 4i cubed minus I over I squared plus I plus 1. So here's a sequence. And so this is a rational function, and we said you can apply the same kind of horizontal asymptote or end behavior rules that we learned in pre-calculus, where we compare the degree of the numerator and the denominator. So here, the degree of the numerator is what? Greater than the degree of the denominator. And so what will happen if you have your biggest power is in the numerator is bigger than your biggest power in the denominator? What will happen to that fraction as I gets big? Yeah. Because for large numbers, say, a trillion, well, this is going to be a trillion times greater than this, right? It's a trillion squared. It's a trillion cubed. This is a trillion times greater. And then that amount, that factor greater is just going to keep getting bigger and bigger. Okay? What about the degree of are the same? So if this were, say, I have a new problem. 4i cubed minus I over 7i cubed plus I plus 1. What's going to happen when I gets really big now?
It'll converge to the coefficient like fraction that forms, like so 4/7.
Right, so for really big values, all the lower powers of I will kind of disappear and kind of go away compared to cubing it. And then, so then as I gets really big, we're going to eventually have this. This will kind of fade away because it's so small compared to this. And then I cubes will go away and will converge to 4/7. So converge to the ratio of leading coefficients. And then if n is less than d, the denominator has a bigger power, then what's going to happen? The denominator is going to get huge.
It'll converge to 0.
Converges to 0. That was the example we had last time. So that was so we can, if you have a rational function, you can compare your powers, and if n is greater than d, that thing will diverge. Numerator will get big compared to the denominator. If n equals d, you take the ratio of the leading coefficients, in this case 4/7. If n is less than d, your denominator will get huge, and the fraction will converge to 0. Okay? We just saw L'Hopital's rule. So here's another technique you can use that we just saw an example of. Okay? Another thing you can do is just list out several terms. Use common sense, use deductive reasoning. You're going to need general algebra and pre-calc knowledge. And like I said, deductive reasoning. Okay, so we have kind of this, there is a kind of a common sense or thinking it through kind of aspect to it. But we also have, right now we have like 4 solid tools: geometric, p-sequence, rational functions, L'Hopital's rule are 4 kind of concrete tools that we have, and we can only use those when they apply, so we have to be good at identifying that. Okay, so let's do examples. Lots of examples here. Okay, so so we're going to write out a couple terms of each sequence just to, so when we get into this stuff about determining convergence and divergence of sequences, we don't want to lose the sight of the fact that a sequence is still a list of values, right? That's always the first thing, first and foremost, that a sequence is a list of values. There we go. So sometimes I think that gets lost when we start, looking at trying to identify it and talking about convergence and divergence. Well, what is converging or diverging? Well, it's a list of values. Either it's getting closer and that list is honing in or getting indistinguishably close to some number, or it's doing something else. That's what we mean by convergence or divergence. Okay, so let's look at this first one. And what do we see about that? You thinking about our toolbox. First of all, -4, 16, -64. What's next? 256. So what do we notice? What kind of sequence is this?
Geometric.
Geometric. It's a value to the index, right? The index is the exponent. Geometric with r equal to -4. Conclusion?
Diverge.
Diverges. It's outside of our range from -1 to 1, where geometric sequences converge. Okay, and you can just see that. You list out the terms, and it's obvious, right? It's exploding, right? The numbers will just get huge. Okay, next one. So what do we see in here? So we got sine of this function here.
The ratio, the denominator and the numerator degree are the same, so we can have the ratio.
Okay, so good. So what we notice here is this argument of sine is rational, like a rational function. And as I gets very big, if you have an n degree of the denominator is equal to the degree of the numerator, and we said that, so therefore this will converge or diverge, just the argument. Converge to 1/3 as I gets large. So if this argument converges to 1/3 as I gets large, what will the sequence converge to? Sine of 1/3, right? So we keep taking sine of these numbers that are getting closer and closer to 1/3, so it'll converge to sine of 1/3. So converges to sine of 1/3. Next one, 1/square root of I. So 1/square root of 1, 1/square root of 2, 1/square root of 3, etc.
I'm sorry, really quickly.
Yeah.
Did you say in the previous problem whether it was a p-series or geometric, or is it actually just called a rational function?
It's not p-series or geometric. A geometric series is r to a power I, like this. It's geometric. A p-sequence is 1/i to the p.
Right, okay, so it's only...
Anything else is not geometric or p-sequence.
Oh, okay, that makes sense. Thank you.
P-sequence has to be like this. Geometric has to be like this.
Gotcha.
Anything else is not geometric or p-sequence. So what we did notice though is, yeah, we have a rational function, and we could use our comparative analysis of the degrees. What about this one?
Converge to 0.
Why?
Because it's a p sequence and p is greater than 0, because p is actually like 1/2, so eventually it'll reach 0.
Yeah, right. So this is the same as 1 over I to the 1/2. 1 over I to the 1/2 is p sequence with p equal to 1/2, which is greater than 0. So as long as, again, as long as p is greater than 0, this will get big, right? This will get big. Our ratio will get small. Okay, so notice I'm writing down work, thinking, justification, and you should do that. You don't just write down converges or converges to 0. So write down how are you thinking about that. What tools are you using? Show all the work that represents your thought process. What about this one? 1, 0, negative 1, 0, 1, 0, negative 1, 0.
Converges to 0.
Converges to 0. These numbers get indistinguishably closer and closer to 0. Is that right?
Diverges.
So by the pattern, you're still going to have 1s and negative 1s at infinity. You're forever. This diverges. Does not get indistinguishably close to one particular number. For it to diverge to 0, in the end, we have to essentially have 0, 0, 0, 0, 0, or something so close that we can't. It's any degree of closeness to 0 that you could pick, you have to reach there and stay within it. So in the very, very end, it's just kind of like just a whole list of zeros, or so close to 0 that's indistinguishable. But this is not that. You're going to have 1 and a negative 1, 1s and negative 1s forever as part of this sequence. Okay. This one. What do we see about this?
You could use the same argument we used for the second one and say that the inside diverges, so that means the whole thing does.
Okay, so that we look at the inside and we have a rational function, right? With how the degrees compare. Numerator is
Larger than the denominator.
conclusion.
Diverge.
That diverges, that gets big. But now, what about the square root? Can the square root save it? So our rational function inside diverges. Square root, makes all those values smaller, but still, even the square root function gets, gets very, very large as your argument gets large. It just gets larger slower. So what does square root looks like? Square root looks like this. And the y values will never level off. Okay, the y values will never level off. These numbers keep getting bigger and bigger and bigger. So this diverges. Because you have a rational function that diverges, square root just makes it diverge slower. That's all. I to the negative 4. Same as 1 over I to the 4th. What about this?
It's secretly like a p sequence, so it'll bring it down eventually to 0.
P sequence. P sequence with p equals a 4, right? I to the negative 4 is 1 over I to the 4. That's exactly what a p sequence is. My p is 4, it's greater than 0, converges to 0. This one, pi to the I over 3 to the I. What do we got here?
Looks like it diverges.
Okay, but for what reason?
Because pi is larger than 3, so to the same power, it's going to be significantly larger.
Okay. All right, good. So you're just saying that it looks like the numerator is going to get bigger than the denominator. Okay? Anything else we can do with this? Can we rewrite this anyway?
I to the I times 3 to the
Okay.
It's geometric.
How is it geometric?
3 to the I.
Yeah, both are to the I, right? Isn't this pi over 3 all to the I? Would you buy that? And therefore R is? And is that in our range of -1 to 1? No, it's greater than 1, right? Pi is bigger than 3, so that's greater than 1. So this is geometric, which diverges. It's just you're multiplying by a number bigger than 1. If you keep multiplying over and over and over again by a number bigger than 1, it's just going to get big. How about this one? Let's kind of do the same thing we did before. So here's a really important thing. So what does 3 to the I plus 1 mean versus 3 to the I? So what would that mean? 3 to the I plus 1 compared to 3 to the I.
3 to the I plus 1 equals 3 times 3 to the I.
So it's, yeah, saying there's one more. This is the number of times. That's the number of times that we multiply this number together, right? That's what an exponent means. It's the number of times that we multiply this number together. We're going to multiply 3 together, I times. So here, if you do I plus 1, it's like multiplying 3 together I times, but then you're going to multiply by one more 3. Right? So that's important that you have a good firm grasp on exponents like that. Like, oh, okay, I'm going to multiply by one more 3 than I 3s. So I could do I 3s times 3. Well, what happens then? So then we got pi over 3 to the I again. It's just that the whole thing is divided by 3. Conclusion? You're still geometric. It's still 1/3. It's geometric, and 1/3 of all the values of a geometric sequence that diverges. Right? So again, the 1/3 slows it down, makes the values less, but it doesn't cause it to converge. Okay? It's just gonna diverge 1/3 as fast. So this is the same. Same reasoning. R is pi over 3, which is greater than 1. So it's a geometric series that diverges. Okay, questions on any of these examples? Okay, I got more examples. So lots of examples here. The thing about this is they're all so different that you need to gain experience, and you do lots and lots of them, start seeing patterns and learning how to apply the tools efficiently. All right, here's a couple more. So what about this one? So here we have what? 2 plus a half. Next term is 4 plus a fourth. Then 8 plus an eighth, etc. Diverge or converge?
Diverge.
People are saying it diverges. So what's at play here? So what kind of sequence is this?
That is a geometric sequence.
So it's not geometric because it's not R to the I, but it's based on, it's actually every term is the sum of geometric terms. So it's not geometric per se, but we're going to use our understanding of geometric sequences to analyze it. Okay, so geometric sequence specifically has to be just a number to I. So by adding them together, it's no longer geometric, but of course it's strongly related, right? And we're going to use that. So this geometric sequence diverges. This one converges to 0, right? So what's our sequence going to do?
Diverge.
Definitely diverge. So adding a little bit more to these values that diverge, even though that what we're adding is going to 0, right? So we're adding on terms that are going to converge to 0, but that doesn't matter. We're still going to be having these 2 to the i's. So it's going to diverge. Because r equals 2 greater than 1. And adding on a series that converges isn't going to help anything, right? That's not going to help anything. Okay, what about this one? 3i plus 5 over ln of I.
I think it diverges.
Okay?
Because if you use L'Hopital's, then ln of I, the derivative of ln of I is 1 over x, and that goes to infinity.
Okay, so he mentioned L'Hopital's rule, so let's make sure it applies. What needs to happen for L'Hopital's rule?
Infinity over infinity or 0 over 0.
Yeah, do we get, so this certainly goes to infinity as I gets big. Does natural log go to infinity?
Yes.
Yes, it's kind of like square root. It's kind of like square root in that it bends down, but it keeps increasing. It never stops getting larger. So yes, L'Hopital's rule.
Professor,
Yeah.
could we say in a way ln of I is converging?
No, it doesn't converge. It gets infinitely large.
So we're not looking at the derivative at all of that.
No, we were going to use L'Hopital's rule and look at the derivative. We haven't done it yet.
Okay. Sorry, I was just a little confused.
Yeah. So we're just talking about why L'Hopital's rule applies. It's because both of these individually get big. So now we're going to apply the rule, and so we say as I goes to infinity. So 3 over 1 over I equals
3i.
3i, which goes to
Infinity.
therefore the original. So since the ratio of the derivatives has a limit of infinity, or gets big without bound, the original sequence diverges as well. Okay, questions on these examples? Okay, let's talk about factorials. Factorials, this is called 4 factorial, and it does not mean 4, yeah, 4, right? What it means mathematically is, it means start with a number, and then multiply down by the next whole number. So you're multiplying down a sequence of whole numbers all the way to 1. So you always multiply all the way down to 1, starting from that number. So 4 factorial is 4 times 3 times 2 times 1, or 24. Okay, by definition, 0 factorial is 1. So you just have to take that kind of on faith. We could have a discussion on why that's true. We don't have time. But whenever you have 0 factorial, that's not 0, it's 1. And there's lots of ways to talk about that. But all right, so what would 6 factorial be? So 6 factorial would be, start with what number? 6. And we're going to multiply down our whole numbers all the way to 1, and that's 720. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 equals 720. So factorials come in to application a lot with like probability and counting things, especially like different orders of things. Just FYI. Oh, by the way, we do not have a quiz today, so we're going to use the last 5 minutes for stuff. So what about 28 factorial divided by 25 factorial? So two really big numbers, right? 28 multiplied all the way down to 1, 25 multiplied all the way down to 1. But because we have this division of 28 factorial divided by 25 factorial, there's a simplification that can happen here. So notice 28 factorial is 28 times 27 times 26, etc., all the way down to 1. And 25 factorial is the same, but starting at 25. So notice in 28 factorial, there's a factor of every previous factorial, right? There's 27 factorial in it. There's 23 factorial in it. There's 3 factorial in it. So every factorial has, as a factor, all the lesser factorials. So in this case, the one we want to focus on is the fact that 28 factorial contains or has 25 factorial as a factor of it. So what happens? So the 25 factorial in the denominator can cancel or simplify to 1 with the part of 28 factorial that is 25 factorial. So what are we left with? Just 28 times 27 times 26, which is a reasonable number, right? This isn't a gigantic number by any means, right? Whereas 28 factorial and 25 factorial are really big, right? But when you do this division, all that's left is 28, 27, and 26 in the numerator. So this is something that happens often, so you be on the lookout for simplifications like this. All right, so we got a sequence. Here we go. We got 2i minus 1 factorial over 2i plus 1 factorial. So to do this, we want to write out what each of those factorials means. Now we got a variable involved, but we do the same thing that we did before. So what's the first number in the product here?
2i minus 1.
What's the next thing we multiply by? So
minus 2.
it's going to be that number minus 1, right? So the next number we multiply by is the starting number minus 1, which is 2i minus 2. And then we subtract 1 again, and we multiply by that. And we're going to do that all the way down to 1. Okay, so what about the denominator? We're going to start at 2i plus 1. That's our first number we multiply here. So what is the next number we multiply by?
2i.
Just 2i, right? 1 less than that one. Then 2i minus 1. And what do you notice now?
It's just going to simplify to 1 over 2i plus 1 times 2i.
So notice within 2i plus 1 factorial, because 2i plus 1 is a bigger number than 2i minus 1, 2i plus 1 contains a factor of 2i minus 1 factorial. Here it is. There's the numerator, 2i minus 1 factorial. So that will cancel out completely with this will go away with the numerator, and we're left with 1 over 2i plus 1 is 2i. And now that looks like one we've done before, or we could even write it out as 1 over 4i squared plus 2i. Conclusion? What do we got there?
Converges to 0.
Yeah, we got a rational. This is, you know, as simple as they come. The denominator gets big, right? So we've got 4i squared plus 2i. Denominator gets big. That converges to 0 as that gets big. So this sequence is equivalent to this sequence without the factorials, right? This is equivalent to this rational sequence here. because we did the math. And we saw that that has a degree of the denominator bigger than the numerator, right? So degree of denominator bigger will go to 0.